Thank you. Thanks, Yasi. Thanks for the introduction. So my understanding is that you did not record such a great introduction, right? So this talk is about MPI and Aurora and Sunspot. However, I need to give a few disclaimers. Well, I'm not talking about MPI really. I'm talking about how to run MPI programs on our machines. So I assume that people who join this conversation know what Aurora and Sunspot is. I will not be giving the presentation about the hardware, though I will be using the knowledge of these machines. And I'm not talking about programming models, though I will have some examples of using a specific programming model for a particular feature that I want to present. So I think that as far as you join this conversation, you already have access to Aurora or Sunspot, and you know the similarities and differences. They assume to be the same from hardware standpoint. They slightly different from system software standpoint. But I think that everything I will be talking here is similar between the two machines. So I will use the term Aurora and Sunspot interchangeably. So let's get started. The very first thing that I advise people to use is the module restore command for both for submit scripts and the login. So everything which is changing very quickly is changing interactively, and it is much better if you start your application from a known setup, from the known environment, and module restore gives you such an environment. Obviously, I assume that you already know that on these machines we will be using modules to create an environment. This is the environment you should expect to see, and a few comments about it. If you see the engineering compiler as part of the one API installation with an old data in it, it doesn't mean it is old. It means that there was the first installation in a certain date, and then there have been updates to it. So if you put it as default, expect that we think it works and works correctly. If you want to change default installations, we assume you know what you've been doing. So please do it only if you really need the latest update. If you don't do a latest update, I recommend do not try to use the latest version. We know there are regressions. This is particularly true for MPI, which is version 51.2, is known to be the last stable version that we advise to use. Some of you may know that there is a 52.2 version. It has several important critical updates, but at the same time, some regressions. So if you are dependent on 52.2, please load that, but remember then you might have certain instabilities. We do advise to use 1.212 Cray Pulse and Cray Leap Pulse, the two modules which provide parallel application level from Cray. This is the level which is actually running the MPI programs for you. Version 12 is critical for us because it contains certain serious updates. Once you have the environment set up, please check that you have MPI wrappers for compilation. In contrast to other MPI, Cray machines, we are on Intel machine, and therefore we are not using Cray specific for CC, 6C capital, and FTN for C and Fortran compilers. We are using MPI wrappers for these languages. You can also see that you've been using the Intel One API compiler and underneath use MPI wrapper with -v capital to make sure that this is correct. The key points: you should have the module restore to make sure that you're running a predictable environment. You should use The models you recognize, you should not update them to the latest versions unless you need. You should use MPI wrappers. If you are on a machine for the first time, do sanity check. Do not try to compile something big like Flash or QMC pack and then complain that nothing works. Please make some simple hello world MPI program. Try to compile it, try to run it, identify what works and what does not. If you cannot do a simple thing, it is very much likely that you will fail with a bigger thing. You will save your time and our time. So try to do something simple, make your own sanity checks, identify the dependencies you have, test them independently. Do not put everything in one place. Do step by step. Remember, these machines are not yet accepted, they are not on production, and therefore they're early access. Things change. Topology of the node. Some of you already know, but I will be using this all the time, so I repeat that each node on our machine consists of two sockets. Each socket contains 52 physical cores. The two sockets are connected. The connection is called UEFI, and this connection is approximately 150 gigabyte bidirectional. This is important. I will be using this information later. The cores are calculated are numerated start from socket 0, continue through the cores on first socket, then wrap to socket 1. So core 52 is the first core of the socket 1. Once we finish the cores on the second socket, the numeration starts over and returns to socket 0, so thread 1. This is because we have hyperthreads on, and that means that every hyperthread is presented as a separate CPU. So we have 208 CPUs and there are 104 cores and 52 cores per each socket. Remember that MPI enumerates CPUs, not cores, or in some sense, people call them threads. Even though it is sometimes inconvenient, but I strongly recommend, particularly in the beginning when the machine is unstable and the system software is changing quickly, use explicit placement of MPI processes and explicit binding them to the cores, and use verbose option of the MPI exec CPU bind argument. So this is an example which binds several MPI processes, 8 in this case, to 4 cores, 4 first cores of socket 0 and 4 cores of socket 1. The slide here would help you understand what the mask means. Some people get confused because the mask's assignment representation is quite confusing even for people who use it very often. Basically, what happens is that the mask represents cores in a bitwise basis. Because the cores are numerated from 0 to 207, each bit in your binary mask represents one core, and some bits are unused on the left. Mask is represented in your printout in hexadecimal number, and the cores are numerated from the right to the left. Each digit in this mask represents 4 cores. Therefore, if you have the 0000 in binary format, that means no cores are placed on those. Then if you have the F6 hexadecimal or 1111 binary, that means that the MPI process is placed to all 4 cores. That's how you understand 0, how you understand F, and how you understand intermediate numbers like 1, 2, 4, and 8. There might be more complex digits. For example, 11 means two cores, core 0 and core 1 is represented by 1, 1 binary or number 3. At the end, I put some more complex example for a 32 core pool where the mask is represented more than 32, and in that case you have a value of 0 0 0 0 0 0 0 0 represented as 0x0, like you see here for values on socket 1. It is better to keep this slide and try to understand something simple first, like place MPI process to core 0, core 1, core 0 and 1 at the same time, and see which mask it generates. And then you will quickly understand how this is represented. It is quite simple, really. The key here is do not imply that your CPU binding works by default. Check that, validate that, particularly if you do scripting. It is very easy to make a mistake in the syntax of the CPU bind command or in the script which generates the placement. The NIC assignment. As you might know, each node has 4 NIC on a socket or 8 NICs on a node. This is important that the NICs are assigned to the socket, not to the node. MPI processes are assigned statically to the NICs, which means that during the initialization, each MPI process is assigned just one NIC, and this assignment stays during the time of a job. Currently, MPI processes do not use multiple NICs. Each MPI process may only use one NIC, and therefore, even if some NICs might be free, they will not be used. However, there is an experimental version where certain MPI commands, certain MPI functions can use multiple NICs from a single MPI at the same time. As you might understand, if you do not use correct assignment, and we will be discussing how to do that, then the available bandwidth from the NICs will be limited to you. Obviously, MPI processes can share the NICs. For example, if you run more than 4 MPI processes per socket, then some NICs will be used. That's why it is important to remember that NICs are assigned to the sockets, not to the node. Even though you might have 8 NICs on a node, if you place all 8 MPI processes on a single socket, they will only be using 4 NICs. Remember that the sockets are connected by the UPI bus, which might be a limitation if you do a lot of communication over this bus. MPI is aware that some MPI processes are placed on the same node and may not utilize NICs but use UPI bus instead. Also, cores are attached to the network on a chip, and therefore, if you place one MPI process on a socket and use just one NIC, you might be unable to use the full NIC bandwidth. The NIC bandwidth is larger than the bandwidth that the core can provide through network on a chip. So you do want to use more MPI processes sharing the NIC than just have one MPI process using one NIC exclusively. So the key, you want to distribute processes across both cores and sockets to maximize hardware. You have to use no less than 4 MPI processes on a socket or no less than 8 MPI processes on a node to use all 8 NICs. However, this is not going to be the maximum bandwidth that you can do from the NICs, because one MPI process probably cannot drive entire NIC. A little bit about the memory domains. Aurora and Sunspot are using the Sapphire Rapid host, the CPU which has both DDR memory and high bandwidth HBM memory. The DDR memory is 512 gigabyte and the HBM memory is 64 gigabyte. The configuration can be determined by using the numoctl command with -h capital before you use MPI exec, so that you know in which configuration you are running. The machine supports both cache and flat mode, where the cache mode uses high bandwidth memory as a cache to DDR, while on flat mode, both memories are available as independent NUMA domains. At the moment, it is recommended to use memkind if you are in flat mode, and if you want to use both NUMA domains at the same time. If you do not want to use to change the application that you've been running, you may try to use NUMA CTL-M2 and 3 to place your application into a NUMA 2 and NUMA 3 domains with high bandwidth memory on the socket. However, you will be limited with memory capacity. The key point of this slide is meet the system configuration with the application that you run and place the correct NUMA choice to maximize the bandwidth available to you. I don't go deep into the detail of memkind use case. Here is an example of the library that I have in my local directory. We do not yet validate the memkind infrastructure and do not have provided on the system wide.
Vitali, we have one question.
Yes.
So I think Dennis is asking, like, should he port the things to 2 sockets versus 1 socket to avoid communication problems?
Ask question again.
1 second, I'm trying to pull. Okay, so it says, if I use MPI program with 2 processes, is it better to assign processes to same socket to avoid inter-socket communication?
So I recommend to use the explicit placement so that you know for a fact whether to use 1 socket or 2 sockets. So use this command CPU bind verbose list 052. Then you will be using 2 sockets. Use list 0 and 1. Then you will be using just 1 socket. Do not imply that there is a default. Do not expect any defaults. That's my advice. Okay. Next question.
That was it. Thank you.
I just want to repeat it one more time. Until machine goes to production, defaults can change at any moment. As far as you want to use the machine, you want to get some results out of it. Do not challenge the machine. Do not challenge us, and do not challenge the software. Just try to be as explicit as possible, as simple as possible, and try to understand what you've been doing explicitly. Then you will get your results earlier, and you will not get into frustration. Of course, it is quite reasonable to expect that the default will probably place the MPI processes on the same socket, but I don't want to state that. It might be different. Or it might be different 10 minutes after I said.
So Vitaly, he's clarifying that he is asking what is faster to use 2 sockets or just one when I have only 2 processes.
What is fastest? I cannot answer this question because I don't know what application is doing. If the application do not use memory, do not use network, do not use GPUs, then it doesn't matter. If it uses network, then placed on the same socket or placed on two different sockets doesn't make much difference because you will be using only 2 network cards from each. If you use memory, then placed on 2 sockets will give you double the bandwidth. If you use GPUs, it doesn't matter, you will be assigned the same number of GPUs. Next question.
I think for now it's good. Thank you so much.
Okay, so I have finished about the flat mode, and this is an example that I ran yesterday using the memkind bench library to validate that it works. I was using the usual stream, and I have measured that if I'm accessing my NUMA domains from socket 0, my means DDR NUMA domain 0, then I am reaching about 240 gigabytes a second. If I use high bandwidth memory, which is a NUMA domain 2, I can observe up to 430 gigabytes a second, or roughly twice more. However, of course, the capacity is less. If I do not use my NUMA domain, if I use the NUMA domain of the second socket, then the cross access is reducing the memory bandwidth to about UPI bandwidth of close to 150 gigabytes a second with some overhead to access the memory. So DDR allows you to access the cross-socket NUMA domain at 121 gigabytes a second and cross high bandwidth memory NUMA domain at 110 gigabytes a second. So this is to illustrate that you want to place MPI processes and use NUMA domains correctly. Use NUMA domains according to the socket that you place. Otherwise, you will have severe heat in bandwidth. GPU numeration. Each socket has 3 GPUs. Similarly to NICs, GPUs are not node shared resources. They are socket shared resources. Because of that, the socket 0 uses GPU 0, 1, and 2. Socket 1 uses GPU 3, 4, and 5. It is possible to have GPUs being seen by MPI processes in a different order, which allows you to have access from one process to GPUs in multiple sockets. This is done through the affinity mask variable. The affinity mask should be used only in a situation when you need to change the default numeration from 0, 1, 2 on socket 0 and 3, 4, and 5 on socket 1. Otherwise, it is beneficial to use application programming interface, depending on the programming model you've been using, to specify what is a GPU and how you access a GPU. In any case, if you use explicit mode, which means that each GPU is assigned as the full device, then you want to have the affinity mask being full integers. Like in this example, the affinity mask equal 4 means that GPU 4 will be accessible to the MPI process. If you use the affinity mask as 0,3, that means that this MPI process will see two devices, device 0 and device 3. And these both devices belong to different sockets. So you need to be aware of how to access those devices, which might have a very different IDs in your program according to programming model you've been using. If you treat each GPU as as two independent devices, so basically each tile is considered a GPU, then the affinity mask is more complex. It should use device and sub-device in enumeration. In any case, explicit binding of GPUs to task is important, uh, and you might probably need it in a situation when you need to have specific binding of certain GPU which do not go in the right stream of 0, 1, 2, 3, 4, 5 in your application. Of course, different MPI processes may know where they are located, and the Pulse interface, the parallel application launcher system, which comes with Cray, provide a few variables such as Pulse rank ID, Pulse local rank ID, which you can access through get-env call and identify which MPI process is calling a specific place and which affinity you've been using for this MPI process. Then, of course, you can split the MPI communicator using the MPI type shared special communicator and understand which MPI processes are sharing the same node. Example is over here. That's how you do that. That's how you identify the local environment. You can keep the slide for reference later. But the idea here is that you can ask the local rank ID. This is the ID of your rank within your node, and then understand how you want to assign the GPUs to this particular rank. And you can have a communicator. In this particular case, I create the communicator shared memory COM with the size of this communicator being the number of ranks per node, and the rank itself should be the same as Pulse local rank ID. And once again, I advise do not imply this is correct. It might not necessarily be correct, though in most cases I've seen this is true. In any case, your application, if you are an application developer, may use this information to identify itself and an environment it uses, and then bind the GPUs correctly. This is the full example of what I was saying with MPI example in this situation. So what this program does is it runs a certain number of ranks, in this particular case 4, in a node, tries to identify itself and assigns specific GPUs to specific MPI processes with OpenMP get num devices, asking how many devices I get available, using local rank ID as an identifier for my rank, and calculation of a device ID that I need to bind to, and then use OpenMP set default device with the device ID of my choice. If I want to use more MPI processes than the number of GPUs available, then the device ID choice with integer division would have the round robin assignment. So this is a full example which can simplify your assignment in OpenMP example. If you use non-OpenMP programming models such as SQL, then there is a number of webinars about SQL at ALCF, so you can refer to that. This is another example of binding the GPUs with the help of the affinity mask, similar to what I just showed with OpenMP, this time using the same assignment but in a shell before you run your program. Remember that the affinity mask should be different for each MPI process, and otherwise it makes little sense. And therefore, you want to assign this the affinity mask after MPI exec is called, but before your program is called. So in this example, I create a set z mask shell script which creates the affinity mask according to the local rank ID. I can specify ranks per node and ranks per tile, or I can specify Pulse local rank ID if I define them after the MPI exec. And then based on those, I can pre-calculate the affinity mask as shown here. This is a round robin here using this fact that I have two uh, uh, I have one GPU being a sub device. So one tile is a device. Therefore, I'm using 12 GPUs on a node. So keep this as a reference for you if you want to run one MPI process per tile. So 12 MPI processes on a node or 24 MPI processes on a node using 2 MPI processes per sub-device. This is for a reference. It is not yet implemented, but we are working on that. We are working on the option to MPI exec to use a rank file option, which is an option which allows you to create a file in a text form and make MPI binding of both cores and GPUs at the same time. When it works, it will basically remove the requirement of specifying the number of processes on the node, the least binding assignment, the affinity mask, which is required to specify the affinity mask, and instead you will just create a single file in the format shown here and give a single rank file command or a single pulse rank file export variable which points out to the file. The format is quite simple. The first column each line represents a single rank, and each column represent certain information about the rank or GPU or a core. So the first column is a rank number. The second column is the host ID, implying that you can specify the file for multiple hosts at the same time. The third column is a CPU or a core ID, and the fourth column is a GPU ID. The GPU can have ranges, and GPUs can have explicit or explicit notation. As of today, this option partially works, and that's why we need the version 12 so that for Pulse infrastructure, so that at least understand certain portions of rank file. The versions prior to version 12 don't even understand this option. We are working to make it correct for all possible scenarios that we envision, and we will be informing our users when it's done. This is coming. I'm coming to GPU awareness. GPU aware MPI is by default. However, if you don't need this, then there is an environment variable or control variable which allows you to turn this off. What exactly does it mean, the GPU aware? It means that MPI message can be located on device memory. MPI can use Z-links to communicate between the MPI processes which share the buffers in GPU devices. MPI may use optimized protocols where message is stored on GPU. MPI may use optimized collective protocols when messages are located on GPU devices. Of course, the GPU awareness takes a price. And one of the things that people already reported is MPI init takes much, much longer. This is important for those people who are running uh, the application in throughput mode, where they run many small MPI processes, each of which is very short, but at the same time, they are running multiple of them at the same time with different data sets. So if, for example, if you collect statistics or you do some training of your machine learning model. So keep in mind that if you do not use GPU-aware features of MPI, then you can significantly improve performance of your application by reducing the MPI init overhead and removing the requirement for GPU awareness with a control variable. At the same time, the latency of certain messages which are placed on DDR might be higher if you use GPU-aware MPI. So if you do not use MPI from the buffers located on GPUs, so you use traditionally MPI only from the host for host-located messages, you do not use GPU awareness of MPI. You can save some from the MPI overhead by removing GPU awareness. Make the right decision. We cannot do a decision for you, only you know what do you use in your application.
Charlie, we have a question with respect to the GPU direct. David Gao is asking, what is the GPU direct? Different PVC GPUs on different nodes could communicate directly or have to go through CPUs on nodes?
GPU itself does not communicate. The MPI calls should be called from the host. The MPI process is located on the host and executed on the host. However, if you use a GPU-aware MPI, the buffers can be located on the GPU memory, and when host MPI process located on the host is calling the MPI command with a buffer located on a GPU, MPI automatically move data in the right way, in the right place, depending on what is the destination of the buffer. Did I answer the question?
Yes, thank you.
Okay. More questions?
Not at this point.
So make the right decision whether you need GPU awareness or not. There are a variety of improvements that have been done during the execution of non-recurring engineering contract by Intel on improving GPU awareness and improving the MPI communication performance, providing that the MPI processes share the same node, so internode communication. As I already mentioned, the MPI is aware that the communication may happen to be within the same node, and therefore, if GPU is storing the MPI buffers, then MPI could automatically use the links which are connecting the GPUs on the node and move data without using PCIe, so presumably much faster. There are many control variables which can tune the behavior of MPI on a single node. I show here the file which contains these parameters. There are lots of improvements in single in host data movement using a variety of mechanisms of shared memory on the socket and between the socket. There is a notion of the fast memory for copying control, which allows also to move data quicker. There is pipelining of internode communications, which means that the messages can be pipelined by the MPI without waiting until the previous communication has been completed. There are many other things which MPI can be used internally for communication within a node, which is in most cases happening underneath, and the users should not really care much about at this point. But if you want to have fine tuning, then you probably want to look at control variables. The purpose of this slide is to tell you that there are many optimizations has been developed by Intel for internode communication operations using the shared memory and GPU infrastructure. And there are many control variables which allow you to fine tune the behavior of MPI. I come to the benchmarks, and there are a few benchmarks that I want to present here. This is an example of moving data from one GPU to another GPU with the help of MPI send, MPI receive, running from two MPI processes on a host and using GPU buffers on devices. As you might see here, I'm presenting latency, running, placing the two MPI processes on the same socket or on a different socket. We have about 2 microsecond cost when we cross the socket, and we have about 2 microsecond cost for small messages. As we increase the number of messages, the bandwidth becomes the most important part. And as you can see here, there is a switch in between the short message and long message protocol, which is happening somewhere close to 512 byte message size. There are certain peaks which show some abnormality, and all these performance improvements are happening as we speak, so this is work in progress. I will probably have a better picture when we come closer to production of the machines. Another example for this benchmark where we present the moving the data by Z-links. In this case, I present very large message sizes, and I show the bandwidth that people can measure when they benefit from MPI awareness of the data transfer. For large message sizes, a single Z-link can be saturated to about 20 gigabytes a second, and all links on a node can be used at a time independently. So as you might know, every tile on our machine is connected through a plane of communication through Z-links, and we have two planes because we have two tiles. So one plane is independent on another plane, and the planes are communicated within a single GPU, as shown here on a picture with an arrow. So technically speaking, you have 10 links, and all links can be driven by 20 gigabytes a second per link at a time on our machine. Off-node bandwidth. This benchmark is designed to show you that single NIC cannot saturate entire bandwidth. Remember, I was saying that you need to use more MPI processes, at least one MPI process per NIC, so that you could saturate all the NICs on a node. So in this example, I am placing the NICs one by one on the same node, and I'm measuring aggregate bandwidth in between the two nodes. One node is sending messages, the second node is receiving messages. Basically, we have linear growth of aggregate bandwidth when we add more and more NICs used. At about 4 megabyte message size, a single core can saturate the link bandwidth, which we have measured about 22 gigabytes. Sorry, there's typo. 22 gigabyte a second is what single link can do through a single NIC. Finally, this example is the reduction latency, and I present this uh, the growth of latency once we start using more and more nodes on a machine. I was able to run up to 100 nodes, basically increasing the number of nodes from a single node where the reduction between within a node is at about 4 microsecond to about 2 cabinets, which is what 104 nodes is about, almost entire Sunspot machine, which is close to about 35 microsecond for a small message size to about 50 microsecond for 256 bytes. It is almost impossible to show the improvements of topology awareness for 2 cabinet size machine once Aurora becomes available for bigger fraction of cabinets, then topology awareness would play significant role in scheduling the communication within each collectives. Right now, I skip it as given, but later on we will update users on how to use collective operations on bigger fractional machine once it's available. Many people are using performance tools, particularly MPI profilers. I am not suggesting that people switch from one tool to another tool. We already have a few presentations about performance tools at ALCF. People can choose in between VTune, Tau, HPC toolkit from RISE. I'm using another tool which came from Bob Volkov of IBM, and I've been using it since Blue Gene time. For those people who know what I've been talking about, this tool is available in my home directory. And as part of this, it also contains MPI profiling in format that you used to use on our previous machines. So if you have questions about this tool, send me a message and I will be happy to help you using it. The key point here is actually that you will have familiar tools on our machines if you are an LCF user since Blue Gene times. My final slide, the final checklist. Everything I was trying to say is try to be explicit, try to use our hardware as much as possible, place your resources and assign your resources in the way that you know how you want to do it because you understand which hardware we provide and how you use this hardware in your application. Use mapping, use binding of ranks to cores, devices to ranks, GPU devices to each rank independently, and always make sanity checks with explicit and verbose placements and information in your job. The key point, search info, send us a message. We are on Slack and we are on support line. We will be happy to help you if you get confused. And this is my last slide. Thank you very much.